and today I'll be presenting introduction and literature review. So in introduction, I'll be explaining about control system and PID control system. So what is a control system? So a control system is described as a group of devices that coordinate, command, guide, or control the action of other devices or systems in order to produce a certain outcome. Proportional integral derivative control, or also known as a PID control, is a feedback technique used in a control system. So this is the feedback system of a PID system. So we have a plant here, plant or a process, and this is P and I, and this is T, and each alphabet. I mean, each process has uh, its own equation, own formula. Review. So in this literature review, I have picked three literature three literature review from a three person literature review. So the first one is the PID control has three adjustable. Okay, so the PID control has three adjustable parameters, one for each control law. So the control law, what they meant was P, I, and D. So the values of the parameters are closely related to closed loop system performance and robustness. So, however, in addition to its simple implementation, setting three adjustable PID parameters is not easy task and has posed a challenge for many authors. And this is said by Kamenko in the year 2002. So, proportional integral. So for number two, proportional integral derivative (PID) control is the most common control algorithm used in industry and has been universally accepted in industrial control. So the popularity of PID controls can be attributed partially to their robust performance in a wide range of operating conditions, and partially to their functional simplicity, which allows engineers to operate them in a simple and straightforward manner. And this is said by C. Godwin in the year 2002. So for number three, it has a simple structure. This is said by two-person, and the person is Zhou and Guo. So they said that PID is a simple structure whose design is model free, and it has ability to reduce uncertainties through proportional action, eliminate steady state offsets through integral action, and anticipate the tendency of the output, derivative action. And in Newton's second law, is fundamentally in modeling systems, which is just suitable for PID control. So that's all from me. Thank you.
So today I will present about the methodology of our group project. So first, we do some research about PID controller and DC circuit in control system. And then we do the introduction and literature review. We find all the components that needed to be in the system. We derive the mathematical model and block diagram for the system using MATLAB and take all the result and put it in table, and then we discuss the results that we get and put it in report. We make conclusion for this project, make video explaining about the report, and make video explain the simulation findings.
Okay, so for today's presentation, I will present to you the mathematical modeling for the electromechanical system for our assignment for subject BAB 30503 control system. So as you can see right now, this is the electromechanical system block diagram. Okay, then over here is the system data or the parameter for the block diagram over here. So now, before we want to do the mathematical modeling, firstly we must identify the DC operation first. So as you can see, this is the DC circuit equation that have been transformed by using the Laplace transform from time domain to frequency domain. So we get here VA minus with the RA IAS minus with the LA IAS minus with the ES is equal to 0 for equation number 1. So we know that E is directly proportional to the angular velocity of the motor. So E is equal to KB times with the delta S. Okay, since torque is directly proportional to the current, so we get T is equal to KAIA. So then we will substitute these two equations into the equation number 1 over here. Then we will get PA is equal to T times with the RA SLA plus with the KB KA theta S over KA for equation number 4. So now we want to find the T over here. So we use this formula and then convert it to the frequency domain. We get T is equal to J S squared theta S plus with the B S theta S for equation number 5. Then we substitute equation number 5 into the equation number 4. Then we get BA is equal to JS square theta plus BS theta plus with the RA plus SLA plus with the KB KA theta over KA. Okay, then next we will find the J total and the B total by using the value of JM, JM, BM, and BN. So for J, we get 0.244 kilogram times millimeter square. And then for the B total, we get 0.0035 Newton meter per radian. And then we get the transfer function is equal to theta over VA is equal to 1.28 over 0.0295 s power of 3 plus 2.7332 s square plus 1.6392 s. Now we move into the manual turning of the PID again. So, so next we want to find the value of K or the critical gain for the system so that we can find the critical period of the system, and then we can use the formula to find the gain for the P, PI, and PID controller. Okay, so for the manual turning, first we must use this formula to find the K. As you can see over here, we find the K, and then we get 1 over 0.0295 S power 3 plus 2.7332 S squared plus 1.6392 S plus 1.28 K. So you can see the characteristic equation of the system is 0.0295 S over 3 plus 2.7332 S squared plus 1.6392 S plus 1.28 K. So from this equation, we can use the Ron-Hurwitz stability criteria method to find the value of K and to test the stability of the system. Okay, so to find it, we must use the Ron-Hurwitz ray first. Yes. See, this is the area that I have arranged. So S of 3, 0.0295, 1.6392, S squared, we have 2.7332 and 1.28K. For S power of 1, we got alpha over here and 0, S power of 0, beta and 0 over here. Okay, to find the alpha, firstly we must use the formula negative 1 over with the A0, A power of 0, A0, times with the A0 times with the A4 minus with the A3 minus A2, A3, A2. Then we get the alpha is equal to 4.4803 minus 0.0378K over 2.7332. Okay, for the beta is the same as the alpha. This time we will use the beta as the denominator. And then we will do the cross multiplication to find the K beta, and then we get the beta is equal to 1.28K. So this is the complete Ron-Hurwitz array. And then we can find the range of stability for K. So first we use 1.28K is bigger than 0. So K is bigger than 0. And then we use this, as you can see, we use this equation 4.4803 minus 0.0378K over 2.7332 is better than 0. So we got here, so after using the solving the equation, we get K is less than 118.5265. So the range of stability for K is from 0 is less than K, while K is less than 118.5265. So we can assume that K is equal to Kc, which is the critical gain. So the Kc is equal to 118.5265. Then we can use we can find the corresponding auxiliary equation to find the S, find the root of equation. Okay, so substitute value of K into this equation. We get here 2.7332 S squared is equal to negative 151.7129. Then we use the square root of the value, and then we will get here S is equal to plus minus J 7.4504. and then we substitute this value into this equation to find the critical period. And then for the critical period, we get 0.8433. Okay, so now we have the KC and the PC. So now we can substitute it into this formula to find the value for KP, PI, KI, KD, and KD for controller P, PI, and PID. So I have substitute the PC and KC into the formula, and this is the value that we get by using the manual calculation for the controller P, PI, and PID.
So, for conclusion, P is the fundamental term generates a proportional corrective control action corresponding to the error. I, the integral term, generates a correction dose whose integral is proportionate to the error. This ensures that the tracking error will be zero if we apply adequate control effort. The control action is brought about by the derivative term D, which is proportionally to the change in the error range. Despite the fact that it typically leads to a lot of control action, this has a stabilizing effect. The type of system you are working with must first be identified, and then this is done will affect how narrow the tuning gains can be. And then since a motor's performance declines with age, it is vital to periodically assess it to ensure that it's running properly. The PID-based approach method perform effectively for the system. The results show that the proposed PID technique takes much less time to solve problems. And it's also, although an internal controller KI will lessen the steady state inaccuracy, the transient reaction might be made worse. That's all from me. Thank you and Assalamualaikum.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So next, I will present about the simulation by using the Simulink in MATLAB. So this is the block diagram that used in this project. So firstly, how to create this block diagram is by using the sum, the transfer function, block diagram, this gain, and again transfer function, and this is also the transfer integrator. This is the inverse gain, which is to make sure this in closed mode, closed circuit. So this is the output and this is input. So next, it goes to the P controller. So in P controller, the the function and the device that uses almost same like the block diagram, the main block diagram, which is some PID controller, which is modified to P controller. Subsystem is when you click on it, it is the block diagram, the main block diagram, which means the subsystem representing this whole block diagram. So close the circuit, close loop, and then this is to get the input from this, get input versus P controller response. So we didn't run yet, so run the so here, as we can see here, the input is 1500 RPM that I set into the step up, which is the input. So this is the yellow one is the P controller signal. So this is the value, the rest time, peak, the overshoot, So next we go for the PI controller. It's same as the P controller. I forgot to mention in P controller, the value that I insert is from the manual calculation that calculated before. Same as the PI controller, the proportional and the integral came from the table from the manual calculation. Insert the value, then view the signal. So as we can see here, this is the PI controller signal response. So next we go for the PID. So this is also the value from the table from the calculation. Let's go for the value. So this is the, as we can see here, this is the input versus response of the PID controller. So it's all for the manual tuning for the PI, and PID controller. So for the for the result without the controller, we can use here. We can write here. So the RPM is set into 1500 RPM. So we run the simulation. So here we can see this is the graph that we got from the block diagram without the PID controller. So next, for the next procedure, I will show the input versus manual PID and versus automatic PID controller. So for the manual tuning, it's the same as the before, using the same graph and value. But for the automatic, I used to tune a different setting by using the automated tuning here, set into transfer function based PID tune apps. So press this tune button, then tune. So this is the graph that created from the automatic tune. So let's show the parameters of the automatic tuning. So this is the exact value. It's the same that I enter in the controller parameter manually. So that this block parameters can be assumed as a automatic. So this is the performance of the cost of the automatic tuning. So after I key in the automatic tune value, so the manual and automatic is done. So we run the simulation. So we can see the result of the response output from the three of them, which is input, manual tuning, and automatic tuning. So as we can show here, so the yellow one is the input, the blue one is the manual tuning, and the red one is the automatic tuning. So that's all for me. Thank you.